Hello everyone, welcome to my presentation. I hope you enjoy it. My name is Ines. I am a PhD student at the Eindhoven University of Technology, more specifically at the Microsystems Research section, and I'm going to give a presentation on my PhD project, which is on the design, fabrication, and characterization of a magnetically actuated glaucoma drainage device with adjustable flow properties after implantation. Here is the abstract that summarizes the work that I've been doing in my PhD project, and I'm going to describe that work in more detail over the course of this presentation. So let's get started. Well, first of all, what is glaucoma? Well, glaucoma is an eye disease that is characterized by optic nerve damage and visual field loss. It is the leading cause of irreversible blindness in the world, with over 70 million people affected. The most important known risk factor for this disease is elevated intraocular pressure, and this is the result of an imbalance between the production and drainage of aqueous humor, the clear fluid that circulates inside our eyes. The aqueous humor is produced at the ciliary body at a constant rate, and then it flows into the anterior chamber and drains out of the eye through some natural drainage pathways. However, if there is some sort of blockage in these drainage pathways, the fluid will then accumulate in the anterior chamber, which will lead to an increase in the intraocular pressure. This high intraocular pressure, this high IOP, can severely damage the optic nerve and does lead to visual field loss and eventually to blindness if left untreated. Just for you to have an idea, in a normal, healthy eye, the intraocular pressure ranges between values of 7 millimeters of mercury and 14 millimeters of mercury. However, in a glaucomatous eye, usually the pressure is measured above 20 millimeters of mercury, which is way above the healthy values, and this can severely damage the optic nerve. And what are the current treatment options for glaucoma? Well, usually ophthalmologists start with pharmacological medication or eye drops, and these aim at decreasing the aqueous humor production or increasing the aqueous humor drainage, depending on the type of medication used. If this is unsuccessful, laser treatment is a second option, and these aims to target specific structures of the eye that are involved in the production and drainage of aqueous humor with the use of a laser to then decrease the aqueous humor production or increase its drainage. If this is still unsuccessful and the glaucoma disease is still progressing, then glaucoma filtration surgery is the last option, and this aims at increasing the aqueous humor drainage only. In this category are included the glaucoma drainage devices. These implants bypass the eye's natural outflow pathways to provide an alternative or artificial drainage route for the aqueous humor to effectively exit the eye, thereby helping to reduce the intraocular pressure. Here you can see some examples of glaucoma drainage devices. The ones on the left side are conventional aqueous shunts. They have a tube plate design. The drainage tube bypasses the outflow pathways, and the end plate sits on the sclera, which is where a fluid pocket will form after the glaucoma filtration surgery, which is filled with aqueous humor. These devices, although they significantly reduce the intraocular pressure, they are associated with very high failure rates and also very serious post-surgical complications. And because of that, a new class of minimally invasive glaucoma drainage devices has emerged. And one example of those devices is the one that you see on the right side, the Percepflow microshunt. These devices are made of superior materials with better designs. They can actually overcome some of the complications associated with conventional implants. They are smaller, they cause less burden to the eye, and because of that, they have a high success rate. Anyway, most of the glaucoma implants, including the ones that you are seeing here, they drain the aqueous humor into the so-called pleb, which is not more than a pocket of fluid that is formed in between the sclera and the subconjunctival tissue or Tennant's capsule. The aqueous humor that flows from the anterior chamber through the implant into this pleb will then be absorbed by the microvasculature present in the subconjunctival tissue that is on top of this pleb, and this helps reducing the intraocular pressure in the eye. Well, although these devices can indeed help reducing the intraocular pressure and reducing as well the disease progression, they are still associated with serious post-surgical complications. And those, the most important ones include hypotony and bleb encapsulation. Hypotony occurs when the intraocular pressure drops to values below 5 millimeters of mercury, and this usually happens in the early period after surgery. On the other hand, bleb encapsulation occurs from weeks to months after surgery, and this is also a very serious complication. I'm going to explain in more detail each of these conditions. Well, in hypotony, the hypermobility of the subconjunctival vasculature due to inflammation, a natural reaction that follows any surgical intervention, leads to the excessive absorption of aqueous humor. And therefore, the aqueous humor production rate cannot really compensate for the high rate of aqueous humor drainage. And this leads to a significant drop in the intraocular pressure that might lead to blindness in some cases. On the other hand, we have bleb encapsulation. This occurs weeks to months after surgery, as I have told, and this is not more than the formation of a scar tissue layer on top of the bleb that blocks the flow of aqueous into the conjunctiva, where usually the aqueous humor is absorbed. And then you can imagine that this will lead to an increase in the intraocular pressure because the fluid cannot be absorbed anymore. And in some cases, the IOP even rises to preoperative values. And this means that the glaucoma filtration surgery had completely failed. These complications, they are usually associated with the design of current glaucoma implants because they are totally passive. They provide always the same fluidic resistance. And therefore, the fluid flow cannot really be adapted according to each patient's needs because some patients might develop hypotony, but others won't. Some patients might develop a very serious fibrotic reaction with a very thick walled bleb being formed with this scar tissue layer on top that prevents the aqueous absorption, but some other patients won't develop this bleb encapsulation. And therefore, what will be ideal will be to have an implant where the hydrodynamic resistance could actually be adjusted according to the measured IOP in each patient after surgery. And this is exactly what we are developing. We are developing a novel smart glaucoma drainage device with flow control properties. This device, the flow of aqueous humor through this device will be adjusted if necessary after surgery and more importantly in a non-invasive way through the actuation of a stimuli responsive valve that is integrated in the implant. Very important parts of this project are to basically fabricate the stimuli responsive valve, which is a magnetically actuated microvalve in our case, and develop smart solutions to integrate this valve into the implant. Another step is to evaluate the flow control properties of the smart implant by carrying out microfluidic experiments. And our final goal will be to produce potential implant prototypes that can be used for animal testing later on. Well, the magnetically adjustable glaucoma implant that I'm working right now is comprised of a drainage tube and a housing element, as you will see later. This implant is made of a highly biocompatible bioinert material called polystyrene block isobutylene block styrene, or abbreviated CIBS. This is a thermoplastic copolymer that the perceptual microshunt that I showed you before is made of. This is a very biocompatible material that causes minimal tissue reaction, and it has been proved to be a superior material that, and it's because of that that perceptual microshunt has very high success rates. Regarding the design of this smart implant, well, as I told, it's comprised of the drainage tube, which has a lumen diameter of 100 micrometers, and the housing element. This housing element is where the microvalve will be integrated. So let's have a closer look at this housing element, how it looks like. Well, the housing element contains the actuation chamber, where the microvalve with the shape of a micro pencil is positioned. as you can see here, to switch between states of valve open and valve closed, we just need to move a magnet below the device, below this housing element, and this microvalve will then move to the open or closed position. When the microvalve is moved to the open position, the device is in a high flow mode. However, if we want to overcome a situation, for example, of hypotony, where we want to restrict the flow through the implant, then we move the microvalve to the closed position, and the outlet channel will then be closed. This is the actuation mechanism of our device. Let's have a look at the fabrication of each of these components that made the glaucoma trainer's device. Well, starting from the magnetic microvalve, this is made of sieves mixed with carbonyl iron powder or iron microparticles of 5 micrometers in diameter. These two components are mixed in a weight ratio of 1:1, and we use the hot and melt extrusion with mixing to mix effectively these two materials. We use this to produce the batch material, the master material that we call magnetic sieves. So we use a mini twin screw extruder where we feed the sieves, pellets, and carbonyl iron powder. We mix these two components for about 10 minutes at 150 degrees, which is the melting temperature of sieves. And after that, we can extrude the master batch material, our magnetic sieves pellets, that we can then use, for example, in the hot embossing together with a mold to then fabricate the micropencil shape that we want. As you can see from the microscopic images, it's possible to conclude that the particles are actually very well dispersed within the sieves matrix. For the fabrication of the micropencil valve mold, we used the femtoprint, the femtosecond laser machining process, which involves modifying a material, typically fused silica glass, by exposing it to femtosecond laser in a design pattern, followed by its etching with a strong etchant such as KOH, potassium hydroxide, to complete the machining process. The micropencil mold that we got from the femtoprint is shown on the top left figure. Having a closer look at the features on this mold, we can see that a rectangular hole was made at the surface of the fused silica glass slide. This rectangular hole opens to a channel that is fabricated inside the glass slide, and this channel ends up in a conical tip. And this mold was used together with the magnetic sieves pellets in a hot embossing machine. Both the magnetic sieves pellets and the mold were sandwiched between two brass plates. They were pressed together at 5 tons, 150 degrees. And at the end, after the demolding step and after removing this rectangular block that is attached to the magnetic micropencil part, we can get the magnetic micropencil valve as the one shown here in the figure on the bottom. Well, the housing element of our device was fabricated from two thermally bonded sieves layers with channels in both sides. The molds for both top and bottom layers were fabricated using the femtoprint, just as before. In the top left figure, you can see the femtoprint mold for the top layer of this device. The actuation chamber is where the microvalve is positioned. You can see as well the micropencil wall, which is where the micropencil valve will have to fit into in order to close the outlet channel. You can also see some alignment pins. They are used for helping in the alignment of both of the top and bottom layers of the housing element. And right now we have as well inlet and outlet ports that are used for the in vitro microfluidic experiments that we are running right now. After the hot embossing step and using this femtoprint mold together with the sieves pellets and using exactly the same parameters in the hot embossing that we used before for the magnetic micropencil valves, we get the replica molded sieves top layer that you can see on the bottom figure. Well, after both top and bottom layers are fabricated, we align the layers and we position the valve in between, and we proceed with thermal bonding of those layers. And when the device is ready, this housing element is ready, we run some microfluidic experiments on this device. The aim of this microfluidic experiment is to evaluate how the pressure upstream the implant changes when the microvalve is moved to the closed or open positions. The setup for our microfluidic experiments consists of a syringe pump, which pumps DI water at a constant rate, 2.5 microliters per minute, which is the production rate of aqueous humor. We have a pressure transducer connected to the inlet of the device, which is constantly measuring the pressure upstream the device. We have X, Y, and Z stages that control the movement of the magnet that is placed below the device. And the outlet of the device is connected to a column of water that mimics the pressure in the blade. So we expect that pressure upstream the device will increase when the microvalve is moved to the closed position. This is what we want, because in the case of hypothony, we want to increase the pressure in the eye because the pressure is too low and it can be very dangerous, can even lead to blindness. So we want to increase this pressure in the eye to healthy values. The result from the microfluidic experiment is shown here. When we move the micropencil valve from the open to the closed positions, we can see that the IOP, or the pressure upstream the implant, can be increased up to 6 millimeters of mercury. This pressure difference is actually sufficient to overcome hypothony, the too low IOP case. And what you can also see from the graph is that the pressure difference varies slightly between open and closed cycles, which might be related with different positioning of the valve into this micropencil wall in each of those cycles. So this is something that we still have to improve. But so far we got a pressure increase that can actually overcome one of the most common postoperative complications following glaucoma filtration surgery. So this is already a very important result that we got so far. Now, conclusions. The magnetic chips batch material was successfully fabricated using the hot melt extrusion process. The femtosecond laser machining process seems to be a very effective technique to fabricate the molds for both the device and the microvalve. And the microfluidic tests have shown that when in the closed state, the magnetically actuated microvalve can provide a sufficient hydrodynamic resistance that leads to an increase in the pressure upstream the implant, which corresponds to the IOP. So this pressure difference achieved is sufficient to overcome hypothony. For future work, leaching tests as well as biocompatibility tests need to be performed on the magnetic chips material. Bonding experiments will be carried out to evaluate the influence of pressure, temperature, and time on the bonding strength of the housing element. And a technique to connect the drainage tube with the housing element, which is the part that we are fabricating right now, will need to be developed. Well, and I would like to end this presentation by thanking everyone that is part of the Microsystems group at TUI. And as my PhD project is part of a bigger project called SIMS, I would like to thank everyone that is part of the SIMS team. And of course, I would like to thank you very much for your attention, and I hope to receive some feedback from you about my presentation. Thank you very much.